and I'm Head of Events and Training at the Geological Society of London. Thank you all ever so much for joining us this evening, which both online and in person, for the fourth event in our Climate and Ecology Off the Rails series. We are delighted to be partnering with the University of Glasgow for this event, and I'd like to say a warm welcome to Dr. John MacDonald for giving us access to this wonderful space as well. For those in the room, should you hear any alarms during this event, please make your way to the nearest fire exit, which is marked at the back of the room, and the fire assembly point is at the front of the building. Thomas Harvey is our Science and Funding Officer. He is sat at the front of the room, and we are just both here to represent the Geological Society, and we will keep an eye on the chat. There will be a chance for both those in the room and online to ask questions, either via the chat function if you're online, or by raising your hand at the end of the event. So without further ado, I will hand over to John, who will discuss in more detail anthropogenic materials and how they link to climate and ecology today.
Thanks very much, Amelia. Sorry to the folks online, not getting the most flattering angle of me due to some AV issues we had, but I think everything is working reasonably well now. So thanks very much for the introduction. I'm a senior lecturer here in the School of Geography and Earth Science at the University of Glasgow. Been here for, oh gosh, approaching 10 years. And today we're going to, as Amelia said, talk a bit about some recent research on anthropogenic geomaterials. I'll get the slide to go forward. Technical assistance here. Let me try that. Nope. Yeah. Ah, what did you press there? How did that work? So it's okay. Apologies for that. Continued technical difficulties. So, like I say, I'm going to be talking about some research that I've been doing more recently in conjunction with many colleagues and collaborators on anthropogenic geomaterials. The question that's on the screen just now might seem like a bit of a weird one if you are a geologist or a geoscientist. It feels like something that's very fundamental to our discipline. But I think maybe some of the stuff that we're going to talk about today challenges some of these questions, like what is a rock? And so I'm going to invite folks online. There's obviously a QR code you can scan to fill in a little Menti poll for us. Folks in the room, if your QR code scanner isn't working for any reason, I've written it on the chalkboard in the room that you can type in manually as well. So I'm going to kind of talk about some more relatively kind of specific research associated with anthropogenic geomaterials in this talk, but there's a chance for some questions on that towards the end. But also maybe chance to have some broader, more expansive discussion based on this topic. Okay, let's get on to the talk proper then. So I'm going to be talking about anthropogenic geomaterials today, and so a term that might not be familiar to many of us. So we're going to start by essentially giving some background as to what these things are, then going to move on to talking a bit about how they kind of link into climate and to ecology, so the kind of focus of this lecture series, and then sort of finish off with thinking a bit about these materials and how they might evolve into the future and how that's of interest to us as geoscientists. So obviously I'm standing here giving this talk, just one of me, but this kind of research that we do and we present on is never done in isolation. So I just wanted to acknowledge at the start, in particular some PhD students that I've been working with in recent years on this topic, Faisal, Jenna and Savannah, and I'll be presenting some of the work done in conjunction with them. Also a range of collaborators, not just at Glasgow, but other institutions across the UK on two big research projects in particular, legacy waste in the coastal zone, led out at the University of Newcastle, and the Resilient Anthropogenic Coasts and Communities project, the big team from Glasgow led out of by Kate Spencer at Queen Mary, University of London. And again, I've put up loads of QR codes and things. If any, I'm going to present various things, links to projects, links to published work where you can read more about stuff. They'll appear on screen. If anyone wants to have a quick look, they can just scan those codes. So, anthropogenic geomaterials, what are they? Not a term that necessarily we're familiar with broadly in geoscience. So anthropogenic geomaterials essentially we classify as things that are solid and they're composed of minerals. So sounds a bit like a rock, but they've been created by humans. They're anthropogenically created. Examples of these kind of materials are actually pretty everyday: cement, ceramics, pottery, that kind of thing, bricks, some well known, like those, some maybe less well known, things like slag, which is a byproduct from smelting. So, for example, making iron and steel, it's the sort of waste product, the byproduct from that. Slags are a particular passion of mine, as some of the students that are in the room and maybe watching online will be aware of. I do talk about slags quite a lot. And they'll feature quite heavily as a sort of example of an anthropogenic geomaterial throughout this talk. So anthropogenic geomaterials are quite diverse, quite variable in their composition. Many of them, such as slag or cement, are alkaline in composition, and that means they typically have relatively high concentrations of elements like calcium and magnesium, which gives them this alkaline composition. Anthropogenic geomaterials are global in their distribution, as you can imagine. Things like, bricks and concrete, and, we use those all the time. But I guess as geoscientists, we're particularly interested with how these materials come into contact with the environment. How are they impacting upon things like climate and ecology, as we're talking about in this lecture series? And so, even though we think about maybe, say, bricks as a construction material, ultimately, they do always seem to end up in the environment, as we can see in this photograph of a beach and the photograph on the left here. Pretty much everything you can see in that beach, sort of cobble to boulder-sized clasts, are made of some kind of anthropogenic geometry. You can pick out lots of the kind of terracotta color in that individual bricks that have originally been in a building, but they've ultimately ended up on a beach in the environment. Now, things like bricks and concrete and cement that end up in the environment in that kind of way are just everywhere. Things like slag, though, which are a waste product rather than a construction material, typically then just get dumped, stockpiled in the landscape. And so they're maybe a bit more easier to map out. And this map, compiled by my colleague and collaborator here in Glasgow, David Brown, just really highlights the global distribution of deposits of these anthropogenic geomaterials. And in terms of numbers, they're globally distributed, but just in terms of volumes as well. If we take just slag alone from iron and steel making, estimates vary, quite hard to quantify this kind of thing, but estimates anything from 500 million to up to 2 billion tons produced globally every year. That's every year. And that's probably only going to go up as development continues in various countries around the world, and there's ever more demand for construction materials like steel, and we end up with this waste product of slag. So these anthropogenic geomaterials, they're quite diverse. How do they actually form? They're all due to human activity, and typically they're created in a furnace. So we're basically taking some natural raw materials and heating them up to really high temperatures to make something else. So with example of, say, bricks, we're taking clay, baking in a furnace at high temperature, changing the mineralogy, and we're making brick. For iron and steel making slags, ferrous slags, taking iron-rich rocks, putting them into a smelter, into a furnace at 1,000, 2,000 degrees Celsius temperature, with some other things like limestone, some kind of fuel to make that furnace operate. And we're trying to get the iron out of those rocks, those iron ore rocks, to make pure iron, to make steel. But there's all the other stuff, all the other elements that are involved in that. And that's what goes into making the slag, our anthropogenic geomaterial, from this particular process. So something like slag, it starts off as a molten material. So it's a bit like a kind of an igneous rock, a bit like lava, really, when it's poured out of the furnace. That then cools. You could maybe think of that as an igneous rock. But often it's sort of granulated into the kind of gravelly material that we see in the photograph on this slide. So when it's then sort of deposited and cools and crystallizes and is left behind at the earth, on the Earth's surface, it's a bit like a sediment, a relatively coarse sediment. And anthropogenic geomaterials, because of this kind of process of typically being created in a furnace at very high temperatures, which are maybe not widely replicated in natural geological processes, certainly near the surface, we tend to find relatively unusual minerals that are not common in nature. I've named a few here. For example, in slag, we find minerals like ackermanite, gehlenite, laranite, merwenite. Any student of geology probably unlikely to have come across these because they don't occur widely in natural rocks. And so ultimately, I guess, as I kind of alluded to earlier, as geoscientists, we're interested in these materials when they enter the environment. You know, I'm not really interested in a brick when it's in a building. But once it's ended up on a beach, like in the photograph here, mixed in with natural sediment and other things, or something like slag, which is in a massive heap of stuff, as we can see in the top photograph, you know, what happens to these materials? How do they maybe have an impact on, in particular, climate and ecology, as we're talking about tonight? Now, some of these materials, particularly slag, you know, it's, as soon as it's created, it's a waste product. And there's a certain degree of reutilization. Some of that gets used as an aggregate for making roads and other things like that. And sometimes you can crush it up and mix it in with cement to make a kind of concrete, but more kind of a circular economy approach to that kind of thing. But ultimately, these things, there's lots of them always end up out in the environment. So let's kind of run through what are anthropogenic geomaterials. So we're going to move on to talk about their relationship to climate first. And I mentioned earlier that a lot of these anthropogenic geomaterials are alkaline in their composition, so they're high in elements like calcium. But they're in these kind of slightly weird minerals, unusual minerals, and that calcium in something like a slag is typically bonded to elements like silicon or a hydroxide, OH anion, and they're not very stable, not very chemically stable at Earth's surface conditions. Kind of not a surprise because they're formed in a furnace at thousands of degrees. But if you then just dump these things on the Earth's surface, they're going to undergo chemical changes. And that might sound like a bad thing, but actually it presents an interesting opportunity for us in a kind of climate context, because the calcium in those slags, for example, would much rather be bonded to the CO2 molecule, carbon dioxide molecule, than it would to the silicon, the oxygen, the hydrogen in the slag when it's first cooled, crystallized. And because of that favorable reaction at Earth's surface conditions with carbon dioxide, it presents an opportunity for mineralizing and therefore removing CO2 gas, either from a waste stream, from maybe a power station or some other industrial processes, or directly from the atmosphere, CO2 that's already in the atmosphere. And so some work that I've done in recent years has kind of looked in very closely to try and understand that CO2 mineralization process. And so using techniques like scanning electron microscopy, we can look really in closely and try and understand what's going on in that CO2 mineralization process. So in the figure on this slide, we've essentially got 4 kind of images from a scanning electron microscope. Panel A, we're looking at sort of just an electron image. The 3 colored ones, B to D, are colored by the distribution of different elements of interest in that same view. And I guess in particular, we're interested in the panel B, the orange one in the top right. We can see sort of 2 zones of relatively bright color. So one up in the sort of top right of the image, which on the in panel A is labeled fresh slag. We've got another bright orange zone down here, which is labeled calcite, and a kind of darker zone in between. That darker color indicates there's a bit less calcium there. And so this is what this is doing, is this is showing us evidence that we've got this calcium-rich fresh slag when it's come out of the furnace, but it's been deposited and just kind of left to do its own thing, Earth surface conditions. And what's happened is some of the calcium has sort of leached out, essentially, through reaction with water from the sort of edge of these slag particles. It's reacted with CO2 from the atmosphere to form a new mineral, this mineral calcite, and that is mineralizing CO2 from the atmosphere. And we can see evidence of that process through this kind of scanning electron microscopy analysis. Kind of delve into that. That was showing the sort of chemical relationships. Also some work recently with Faisal Kadur, a PhD student here in Glasgow, looking at the mineralogy of that. And we can see in the two panels A and C on the top left on this slide, we've got a kind of pink color. That's our sort of fresh slag minerals. The blue color of the calcite that's mineralized, that's CO2 from the atmosphere. And there's a kind of bit less, but sort of yellowish zone in between. That's a different mineral called pseudoballastonite, which essentially is formed when that calcium has been leached out of the slag. So that's kind of 2D approach that we've used to try and understand this process. We can also do it in 3 dimensions using a CT scanner or micro CT scanner, really just the same as the one you would get a scan in hospital, just a bit smaller, designed for looking at rocks and related things. And these sort of 3D block models on the right, essentially just showing that we can use this technique to look inside these pieces of slag and understand, where is the CO2 going? Where is it being mineralized? And we can also then use the software associated with this micro-CT to do clever analysis to do things like quantify, how much CO2 have you mineralized within a certain size or volume of piece of slag. So I guess we would try and summarize some of that data in a sort of cartoon schematic model of what's going on. And this diagram at the bottom here, we've got some fresh slag, but that then comes into contact with water and air, and you have this reaction going on where you end up with essentially sort of buffer zone of what I've called reacted slag, where the calcium has leached out, and that's then gone into precipitating, forming the mineral calcite. That's taken in CO2 from the adjacent air. And so, we collected this data just by looking at slags that have been just dumped, left in a heap near the steelworks. And that's kind of just happened passively. But actually, there's a lot of research ongoing that shows that you can take this material and really kind of engineer that process to speed it up, maximize the amount of CO2 that you can mineralize. So it presents an interesting opportunity as anthropogenic geomaterial for maybe kind of offsetting or mitigating some of the effects of anthropogenic climate change in terms of the amount of CO2 in the atmosphere. I guess also in terms of a kind of maybe slightly different aspect on climate, if you were to ask me maybe, I don't know, 8 years ago, when I did my research on natural rocks, if I would ever collaborate with researchers from other disciplines, like in social science or something, I'd probably laugh in your face. But one of the beauties about looking at anthropogenic geology, or anthropogenic geomaterials, is amazing. It's opened up all these opportunities to collaborate with people from other disciplines that I'll kind of touch on in various points throughout the talk. One interesting one recently has been with sort of social science, geohumanities, we might call it, sort of human geography, through the work of a PhD student that's just finished, Jenna Kirk, who is a social scientist and humanities researcher by background. And, I was kind of going to these places with these big slag heaps, but they were just sort of there. There was no other evidence of what had created them. The steelworks are long gone, and, we see that widely in the UK and in Scotland, long history of steelmaking around Glasgow. You won't find any of it now, but you will often find pretty much the only legacy of that, or tangible physical legacy of that past industry, is the slag heap this just byproduct that was just dumped and left there. And so there's some really interesting research through things that I would never think about in my research, like poetry or interviewing people who used to work in these places, to think not just about the past, but also think about, how do communities who, scarred by deindustrialization, what do they now think about this material that's still there? How do they view it? Is it positive? And actually sometimes challenging their views by showing them the CO2 mineralization stuff that I've just talked about. Actually, you've got this kind of stuff that you don't really like because it's an unsightly waste material in your community, but actually maybe there's a positive opportunity there that could lead to, investment, jobs, etc. So it'd be really interesting to think about that, and I guess we get people to think about, well, actually, there's maybe a certain element of guilt, of people that worked in these industries. Like, oh my God, we were doing this stuff and it pumping out huge amounts of CO2 that we didn't realize at the time was a really bad thing for the climate in general. But actually, maybe we've got this opportunity still here to, make some kind of contribution to mitigating climate change. So that's a couple of sort of aspects on climate. Ecology, I guess, being the sort of other key part of this theme of this lecture series. And, the two are not necessarily totally distinctive. They're linked to a certain extent. And perhaps, when what are anthropogenic geomaterials are typically kind of waste human-created things that end up in the environment. Probably your first thought will be, oh dear, that's not very good. That's probably going to cause some pollution or something. And that is, a focus of a lot of ongoing research to understand pollution risks from these materials. So again, if we take slag from iron and steel making as an example of one of these anthropogenic geomaterials, in the legacy waste, the coastal zone project that I mentioned at the start, one of the things we did was to do a sort of mapping exercise. Say, well, actually, where are these old dumps of this stuff that tend to be forgotten about? So work led by colleague Alex Riley at the University of Hull, part of this project. It's a really neat mapping of these slag deposits that are still out there in the landscape in the UK. And that was really useful because it kind of then enabled some focusing in on, well, are there certain areas that have got a lot? And sort of around Glasgow, North Lanarkshire, was one of the highest. Although interestingly, Cumbria, not somewhere we would necessarily think of as a very industrial place. Huge legacy of steelmaking in West Cumbria, places like Workington, Barrow-in-Furness, Maryport, towns such as that. And actually, as a result of that, Cumbria is the place that has by far and away the most amount of slag left in it. So this mapping is good because it maybe allows us to focus in and think about, okay, well, where's there most of this stuff? Where might there be the most risk of pollution to the environment, which would then harm the ecology in that place? So, and associated with that, doing kind of some chemical analyses, what we call a leaching test, essentially take samples of this stuff and reacting it with different fluids. So we did it with deionized water, so it's really pure water, not very representative of nature, but we also did it with seawater as well, and looked to see how much of toxic metals of interest that could be harmful to the ecology were leaching out of these materials. And so the graphs on the right of the screen, we can see there's 6 different graphs, one each for different metals of interest. So things like chromium, vanadium that are of particular interest and relatively high concentration in slags. The work done by Alex, Catherine Gandy at Newcastle, various other people involved in this project, we kind of were able to show, okay, what's the kind of risk here, relatively high concentrations compared to safe levels, and those kinds of things. So pollution in the form of ecotoxic metals, which are harmful to living things, to ecosystems, to biota, are a challenge to the ecology posed by these deposits of anthropogenic geomaterials, but not just chemical risk as well. There are sort of physical properties of these materials which can be challenging for ecology as well. Photograph on the left is a slag heap in Barrow-in-Furness in West Cumbria. And we can see kind of towards the right of the photograph is the mudflats. And that was the sort of environment, the habitat before the iron and steel making came along in the sort of late 19th and into 20th centuries. But then, of course, that got going, created a huge amount of slag and dumped that. So you radically altered the physical characteristics of the habitats in that area. And so that then poses challenges for recolonization of species in that area. You're going to change the kind of ecosystems that you have through the deposition, the dumping of this very different materials, gravelly, quite porous, very rough, angular material. It's not just these kind of uniform deposits of materials like slag. If we even go to just kind of old rubbish dumps, old landfill sites, where we have quite a range of materials, some of them are anthropogenic geomaterials, others are maybe not mineral, other kind of plastic-based waste, those kinds of things. In the other project I mentioned at the start, that's just kind of started this last year now, on resilient anthropogenic coasts and communities, we have a focus on looking at landfill sites of mixed composition, of which there's a lot of anthropogenic geomaterials in them. And from some early fieldwork we did down in the Thames estuary, I just put this photo in on the right because I've never been to a beach like it. This is a beach on the Thames where an old landfill site is being eroded by coastal erosion. And pretty much everything you can see in that photograph on the right is anthropogenic in some form. This beach is made of bits of brick, horribly angular bits of broken glass. As you can see, angular shards of pottery, ceramics, there's plastics in there, a huge amount, there's some slag, bits of brick, there's a huge amount of old, really weathered batteries, which is pretty nasty. And so you can kind of imagine, well, this is a pretty unfavorable environment for an ecosystem to develop. You've got these kind of, particularly maybe for larger animals that could be affected by these kind of, really angular bits of material, lots of broken glass in that as well. So, in a lot of instances, these anthropogenic geomaterials are somewhat challenging, let's say, for ecology. However, not always. Sometimes they can actually be a very positive thing for ecosystems and habitats. And so work done over the past few years by another PhD student, had the pleasure of working with, Savannah van Mesdag. Again, this is another nice collaboration story. Savannah's a botanist, so studying plants by training. But, here we are collaborating, a geologist and a botanist, with a particular focus on plant communities that develop on these newly created deposits of anthropogenic geomaterials. So one of the key things about them is their physical properties. So something like slag, as you see in this photograph here, it's a gravel. And in particular, it's an alkaline composition gravel. And so that's not a kind of common set of properties, particularly in the UK. We've got quite a lot of limestone bedrock if you go to maybe the north of England, Pennines, that kind of area, but it's rock, it's sort of solid rock. Whereas this kind of gravelly sediment with an alkaline composition, that's very unusual as a habitat in the UK. The chemical properties as well can lead to interesting ecosystem development, principally because of the elevated concentrations of metals such as chromium and vanadium, which you find in higher concentrations in slag than you do in natural soils and rocks on the whole. So these can actually be interesting materials or substrates, as we might call them, for plant community development, but then also leading into invertebrates, higher animals as well. So these kind of sites have these sort of brownfield sites that are underlain by these anthropogenic geomaterials, typically form what we call an open mosaic habitat. So in the photograph here, this is a slag deposit from the kind of mid-20th century, again in West Cumbria. We can see in this photograph there are patches with the kind of pale creamy color, which is just the bare slaggy gravel. But we've also got bits with a kind of very low level, maybe mosses or lichens growing, some of these kind of patches with the sort of brownish color. There are some patches where there's some sort of grass development, maybe a few other plants. There are then areas with sort of low level shrubs, maybe flowers, through to full-blown trees. And it's this sort of patchwork of sort of microhabitats within one site, this open mosaic, as we call it, that actually then is also relatively unusual. Even in rural areas, we're kind of prone to relatively monoculture habitats in the UK, where you have a lack of sort of variable levels of cover, trees and other bushes. These kind of abandoned, one might say, kind of brownfield sites, which are underlain by these anthropogenic geomaterials, often give rise to this quite variable levels of cover, and that can lead to great species richness, both in terms of the plants that grow there, but also the animals, the insects that are able to colonize these different sort of microhabitats within an individual site. And so actually of interest, you might think, oh, brownfield site, there's some industrial waste there. Oh dear, that's not very good. Actually, all these sites are designated conservation sites, are protected in law, SSIs, that kind of thing, precisely because of their species richness due to this open mosaic habitat. And it's funny, we hear from politicians a lot about, oh, yes, we're not going to build in the green belt, we'll develop some brownfield sites. That's much better. But actually, in many places, the green belt, the kind of maybe agricultural land surrounding cities and urban areas, is relatively ecologically bland, let's say, or limited compared to some of these brownfield sites which have this kind of range of habitats. And so the kind of work done by Savannah and others in this kind of space, documenting the species there and trying to understand maybe some of the links into the chemistry and the physical properties of the slag, it's really important for then, hopefully maybe driving forward into policy agendas around development and construction on these kinds of sites. So these ecological niches or sort of microhabitats in these kinds of sites, which are underlain by anthropogenic geomaterials, lead to a range of, or maybe a broader range of species are able to thrive in a more uniform habitat. They could often also include ones which are maybe more tolerant of things like higher levels of some metals like chromium or vanadium that would otherwise be outcompeted by other plants on something like just a field or a grassland or that kind of thing. And so we see interesting plant species that Savannah and I documented on fieldwork associated with a PhD, various different types of orchids that do very well on some of these alkaline slag-based things. The one on the left is a carline thistle, so a less common species of thistle. It's not just plants, though. These anthropogenic geomaterial sites are very good for invertebrates as well. Range of different butterflies and moths, burnet moth, like in the photograph at the top. Grayling butterflies, not common in the UK, but seem to do particularly well in these sites, even relatively far north in places like Cumbria than they might do otherwise. Also birds. The photograph at the bottom is, again, this is a historical slag deposit in West Cumbria. This is the RSPB Hodbarrow Reserve, so it's an RSPB reserve. Even though this is a dump of human waste, essentially, this slag, this is so valuable for, in this case, birds, that the RSPB have taken it over and manage it. So this is the sort of Dundon Estuary, so you're kind of down in the far southwest of Cumbria. Looking into this photograph on the bottom, the sea is just behind you. Morecambe Bay, very important habitat for many birds. the slag has been was sort of carelessly dumped into a lagoon, which formed after the mines that the iron came from flooded, and was left there. And there's, as you can see, there's sort of an island of slag in the middle, but actually that's ended up being a fantastic habitat for ground nesting birds, some of them quite rare. Some varieties of tern, sandwich tern, little tern, do particularly well at RSPB Hodbarrow. Again, the sort of alkaline composition, lots of calcium is good for shell growth, shell development, eggshells. And this island in a lagoon made of slag, protection from predators like foxes that might come and eat its eggshells. So actually these kinds of sites underlain by anthropogenic geomaterials can be really valuable for ecology in terms of their habitats. So I guess the sort of final section of the talk, I want to talk about some aspects of the kind of future of these anthropogenic geomaterials, one of which is we often find them at the coast. A lot of the photographs I've showed of these sites have been at the coast. And that brings challenges in the near to medium term future, with climate change accelerating levels of coastal erosion, coastal flooding. With coastal erosion and coastal flooding of these kinds of deposits, you're then releasing these materials out into the wider environment, maybe some of the toxic metals within them, that then poses harm to biota and ecosystems. And some of these sites are not very well known or protected. And so the work Alex Riley, I mentioned earlier from the University of Hull, is part of the Legacy Coastal Waste Project. Again, his kind of mapping work really neatly showing, in this case, just for England, that was due to the central availability of data. That's another story why we don't have it for Scotland, but anyway, showing that actually some of these different types of waste materials, many of which are made of, at least partially, if not fully, of anthropogenic geomaterials, like, you know, iron and steel slag here, then got various mixed spoil, mixed 60s, undefined, mixed, you know, a wide range of categories that were recorded at the time, likely to have anthropogenic geomaterials in them. And on these kind of bar charts, we show there's a relatively uneven distribution around England, but in terms of the colours, many of these are unprotected. So they're vulnerable to coastal erosion and flooding, and therefore potentially impacting upon ecology. And so trying to really kind of understand where those are, doing some kind of risk assessment around sites to perhaps prioritize these unprotected sites. That's not good, they're unprotected. We should probably protect them, but you know, it's pretty expensive to build seawalls. Engineered solutions, these are maybe not the kind of things that we can let go in kind of managed realignment type approaches to coastal defense. And so this kind of work to show really just where these deposits are, certain concentrations of them in certain places, like in actually along the kind of Northumbrian, County Durham coast in the northeast of England. Lots of potential unprotected deposits there that may pose a risk to the environment. And also kind of going forward into this other big research project I mentioned, the resilient anthropogenic coasts and communities, we're also thinking about how maybe human communities as well as ecological communities could be at risk from these materials. Not all negative though. Final thing that I want to talk about is a sort of pet subject of mine, which is a sort of different way of thinking about the future of these anthropogenic geomaterials. So, as kind of shown in a lot of the previous photographs, you get a sense that they're like sediment, plastic stuff, whatever it is, slag or something else like that. But we've started to find in research that I've done in collaboration with a couple of colleagues here, Amanda Owen and David Brown at the University of Glasgow, places where these sediments are turning into larger, let's say, rock-like masses. So you're having lithification of a sediment to rock. And so in the photographs here, this is the slag heap down at the former Glengarnock Steelworks in Ayrshire, just near Glasgow. And the material in the photograph on the left is slag, but that slag has undergone some change, some chemical change and some physical change to go from essentially gravel to what is essentially a sort of rock-like platform that the rucksack in the photograph is sitting on. And if we kind of look at that a bit closely, cut a section through it, we can still see the sort of gravelly texture of the slag in the photograph on the right, but that's been bound together by new minerals forming. So what's going on? What's going on there? Some work we've done recently, again, back to West Cumbria, rapidly becoming one of my favourite places to go for fieldwork. Coastal slag location, so the slag's dumped right on this is the Irish Sea, just in the sort of left of the satellite image here. So we're quite an exposed coast, massive slag bank, probably the biggest in the UK. Just waste just being deposited, an over 120-year period. And what we see there is, in the photograph on the right, this kind of, it's rock, looks a bit like what we might, as geologists, think of as a conglomerate, but of course clasts, except every clast in there is made of slag. Not like a conglomerate where your clasts are made of, I don't know, sandstone or granite or some other rock. And we can see layers of this stuff building up. Everything you can see in the photograph on the left is a rock, or what I would call a rock. Come back to that. It's clasts of material lithified together. And we can see that what's happened is, this is on the coast, on the Irish Sea, quite an exposed coast, lots of waves, tide energy. The waves have eroded the slag, rounded off the particles. So analysis done by my colleague Amanda, a sedimentologist, shows that the particles of slag are relatively rounded compared to what they were like when they were first deposited. And then if we go back to the scanning electron microscope, showed some data from that much earlier on in the talk, essentially what we can see here is these sort of multicolored class of the kind of rounded particles of this kind of greeny, purpley, pinky color. They are, let's say, sub-rounded particles of slag. But there's also then this little network of sort of orangey color in between all of these. And this is that mineral calcite that I mentioned earlier on, which is forming, in this case, as what we call a mineral cement, binding those particles of slag together. Same kind of thing with the atmospheric CO2 mineralization for climate change mitigation that I talked about earlier. Calcium leaching from the slag, reacting with CO2, forming this mineral. But in this case, rather than just a wee coating on individual bits, it's actually binding them together and making them into a rock. So just kind of summarize that process essentially in this sort of four-part diagram. We've got reaction with, or contact between the slag sediment and water. That could be in a pond, but it could equally be from the sea. That reacts with the slag, calcium comes out, reacts with CO2 from the atmosphere, you form a new mineral, this sort of orange color, filling in the gaps in between the slag particles. Why are we interested? This is seems very scientific, kind of fundamental. Why are we interested? Well, this has got applications for things like ground stability, potentially immobilizing pollutants, metals that might leach out of the slag. We're capturing CO2. Could also be something that could be harnessed for defense against erosion, maybe coastal erosion. Could be creating new ecological niches, these sort of new rocks forming around these anthropogenic geomaterial deposits. We see kind of slightly unusual looking communities of seaweeds and algae growing on them. Get some more ecologists involved in helping to pick those apart. And then I guess kind of fundamentally, perhaps going back to the question that I talked about or mentioned with the Mentimeter poll, is this a rock? Would you call it a rock? New kind of rock? Don't know. We'll maybe come back to that in the discussion. So final slide, just to conclude. Anthropogenic geomaterials, what are they? Human-created mineral materials, often byproducts such as slag from industrial processes, but also things like everyday things like bricks, ceramics as well. Present opportunities for us in terms of climate, for carbon dioxide removal, so mineralizing CO2 that was in the atmosphere, but also recording social legacy of past industries. In terms of ecology, challenges through release of toxic metals, pollutants, but also providing these opportunities in terms of unusual species-rich habitats. And in terms of the future, potentially uncertain due to flooding and erosion, particularly at the coast, but an interesting avenue of this lithification, what's going to happen to these materials? Are we forming new kind of rock? Okay, that's me. Thank you very much.
We don't have any questions online. I don't know if anyone's got any questions in the room. Yes.
Thank you very much for that. It's really interesting. To what extent are the processes you're seeing, like the lithification in Cumbria, site-specific based on perhaps chemistry or conditions on site, or widespread and likely to occur elsewhere?
So I'll just repeat the question with the microphone over here. Folks online, so the question from the audience in the room was pertaining to the lithification of the slag deposits that I kind of talked about in the last few slides. Is it sort of site specific, or are there maybe more common parameters or things that might mean this could happen more widely? So that's a really good question, and one that I hope to be answering in the coming years. It's actually quite new stuff that we've really only done in the last 12 to 18 months. Based on what we can kind of understand from the sort of microanalysis that we've done, the sort of scanning electron microscopy, the chemistry, the mineralogy, those kinds of things, it seems to be that, we've kind of focused on slag so far, which is a calcium-rich material, and you definitely need contact with water and air. I would say you've got a source of CO2 in the air and some water. The reason I'm also kind of confident of saying that those two things are important, because I know that, colleague Phil Rensforth, who's now based at Heriot-Watt University, maybe about 10 years ago, maybe not quite that long, drilled a borehole using kind of geotechnical engineering rig, deep down into an inland, but quite large slag deposit, quite deep. And at the bottom of that borehole, they found it was dry. There was no water, and there was no lithification. It was just gravel. So certainly contact with air and water seems to be key. Quite how deep that can percolate into a deposit of this stuff, we're not quite sure. The deepest we've seen is at the site at Glengarnock in North Ayrshire. The North Ayrshire Council have redeveloped it into a kind of a slag heap, into a sort of public park type thing. So they built some paths. They needed some tarmac walkways. They needed to dig drainage. So the digger drivers who were creating the drainage ditches around these paths reported that it was the worst thing they'd ever done, because it was like they were expecting sediment, but it was about at least a meter, if not more, of this sort of lithification going down. So there's obviously a certain degree of percolation in. So that's a long way of saying the two key parameters seem to be, well, three. Well, do you have slag? So yes. Do you have water, and do you have air? Another possibility is that there might need to be some kind of dynamism in the system, some kind of energy, perhaps. Because we observe this at pretty much all of the coastal and indeed inland slag deposits we've been to in the UK, which are in contact with water, apart from one at Barrow and Furness. And the difference there is that is behind a mudflat and a barrier island. So it's quite a sort of hydrodynamically calm situation. So that's our kind of hypothesis so far. But if I was a betting man, I would bet you some money that if you went to any, let's say, coastal iron and steel making slag deposit anywhere in the world, you would find lithification. And I hope to do that if somebody will give me some money to go to some nice places around the world to test this.
Two more questions.
Oh, yep.
Got one, I'm going to read it out.
Yep.
Easier. So you mentioned that many of these anthropogenic materials are more reactive than natural rocks, and gave some great examples. Do we have an idea of the rates of these processes and the long-term stability of some of these deposits? Are they only getting more stable? That's the first question.
Okay, that's a good question. It's a tricky one to, well, I guess it depends how long term is long term, because these things have been the more reactive ones, let's say the kind of iron and steelmaking slag, cement, concrete, how long have they been around for? 150 years, maybe, in the case of certainly the kind of large scale manufacture of iron, molten iron steel. So quite hard to pin down rates, but I would say yes, they're probably definitely moving towards a more stable form. Again, if we take slag as an example, sorry, I keep going on about slags, pet subject. The chemical reactions are relatively fast. I mean, I've observed, collected some fresh slag, just left it on the side, like on my desk. So it's just got up with the air, Scottish office air, so it's probably quite damp as well. And that will have a skin of calcite on it within months. We can accelerate that process in a kind of engineered reaction. We grind the stuff down into very small particle sizes, put the temperature up, add in loads of water. You can engineer the rate in a way to be what you want it to be. But in terms of moving towards a more stable form, absolutely. Because the calcite that's forming as the reaction product on the slag anyway is a more stable form at Earth surface conditions than the minerals in the slag itself. Interestingly though, when you do that, it only goes so far. If your piece of slag is large enough, pebble size, the reaction will only go so far and then stop because the calcite that forms blocks the air and the water coming into contact with the fresh slag. So that's kind of good. It's sort of armoring it and stopping stuff getting out, nasty things getting out, toxic metals. But if you were to then disturb that, either mechanically, grinding it up, or it gets mucked up on a beach or something by the tide, by the waves, or if you had some kind of chemical change that caused, quite extreme chemical change that caused the calcite to dissolve, then you kind of come out of that, I don't know, almost like a metastable state. It's achieved some kind of stability, but that could be changed.
Excellent. So then we have a two-part question from our lovely climate and ecology lead, Steve. So question one, are these slag heaps viable as carbon capture mediums large enough?
Okay, I can answer that. They could be. It's a difficult question to answer. It's one that people ask me actually now and again, actually quite a lot. How much CO2 could we take out of the atmosphere? How much of a difference could we make to, how much of our targets for net zero could we achieve by doing this? And I was like, well, how long is a piece of string? There's a lot of moving parts in this. It's the same kind of range of parameters. If you were to go in and dig up these slag heaps, which are big mounds, you're going to dig them up so that the CO2 from the atmosphere could percolate and react with all of it. That would be good, but you probably expend a lot of CO2 digging it up. Equally, if you were to grind it down into a nice fine particle size, that'll make it really reactive, but slag is really hard. So it takes a lot of energy to grind it up, so you're probably going to emit quite a lot of CO2 doing that. So there's an interesting balance to be achieved in these things. I think with fresh slag, as it comes out of the furnace, which is not really going to be in the UK anymore, but in China and Mexico and India, steelmaking centers, Vietnam, those kind of countries. What would be good, perhaps, is to design your slag impoundments, your slag heaps, in a certain way that is relatively low intensity, low energy, but maximizes the amount of CO2 that you can passively mineralize without putting any more energy into the system and expending CO2 from that. So difficult question to answer. Yes, I think, we might as well. Let's face it, cutting emissions is hard. Still need to do it. But let's just use anything we can to help with offsetting, the dirty word offsetting. But, let's do what we can. All these things can help, even in a small way.
And a last question from Steve. Could some slab deposits be mined again to generate material for carbon capture industry?
Yes, I guess that's kind of maybe related to answer in relation to the first question. Yes, but you need to be very careful with your carbon accounting as to just how much CO2 you expended to dig it up and mine it. Work has been done actually to look into other opportunities that the slag might present, not just for CO2 mineralization, but also as a kind of what we call resource recovery. So, you know, we know these slags have got toxic metals in them, but those toxic elements are actually useful for things, green technologies, for example. But in slags in particular, they're kind of a bit awkward to get out or quickly and at, you know, reasonable amounts. So strong chemicals may be needed unless you're very patient, which we're not. And so it was deemed when that work was done, maybe in the kind of mid-2010s, that it wasn't currently economic, but was, you know, various technological developments. They could become a resource for metals that we need for green technologies, for example, green transition. But then I suppose a counter to that is certainly in the UK, not a great source for us because most of these legacy slag heaps are protected for their ecological values, kind of talked about in some of the talk as well. Back.
Just when you're saying that you can't really dig them up, what is the sort of porosity / permeability of the slag if you want to do sort of well injection instead?
That's a good idea. So the question from the room, just for the folks online, about the porosity and permeability of these slag deposits, thinking about maybe injecting CO2 into those. The porosity and permeability of an individual particle of slag is very high. It's very porous, cools very rapidly, so lots of vesiculation, a bit like a pumice in a way, or some other natural igneous rock that cools very rapidly, and often, you know, a lot of air is trapped within that. Similar kind of thing with slag. Interestingly, though, if you look at a slag heap as a whole, because of this kind of lithification process that seems to happen quite widely, again, you tend to get a bit of a sort of an armoring on the outer surface over time, which reduces the permeability, certainly from the outside, the atmosphere, into any sort of deeper parts of the slag deposit. But if you were going to maybe then drill a well or two to inject, yeah, I think that would be an interesting thing to explore, actually. Again, you need to think carefully about your carbon accounting of drilling a well. Hard stuff. And I think almost like, so I suppose in a way, a bit like CO2 injection into natural rocks, be they sandstones or basalts or whatever, you probably want to do a lot of characterization like we would do in natural reservoirs for CO2 sequestration. So you want to be trying to understand the 3D architecture as their sort of structures, as their stratigraphy, even in these deposits. There are some hints of that from looking at sort of outer surfaces, but I don't think anyone's ever really, I don't think anyone's done any seismic or something like that on a slag heap. That'd be very interesting, actually, to think about that. Good question. All right.
Show that map of the like the mapping of the slag distribution around, I think it was mostly just England, but how do you go about mapping like something like that? Because I'm, you know, when you hear the word mapping as a geologist, think, you know, like outcrops in the ground, but surely there's a lot of this subsurface stuff. Like how much of this is from just knowledge of what's in there in industry, and how much was there like, do you actually do like subsurface, like ground investigation and stuff to kind of characterize that? Because I noticed that, yeah, there's a lot of stuff that's been covered over, as well as the stuff that's like opened up. So how do you count the stuff that's not like obvious on surface?
Thank you very much. So just for the folks online, question from the room to do with the mapping of the distribution of deposits of anthropogenic geomaterials, in this case, slag in the UK. So that was the work that I showed, the mapping work from Alex Riley from Hull as part of the Legacy Coastal Waste Project. How did we do the mapping, essentially? You know, so a lot of it was done through, like, remotely, essentially, using Google, for lack of a better explanation, is, you know, where were there iron and steelworks in the UK? Reasonably good records of that. Don't need to go back so far. A lot of it's tied into the distribution of where kind of iron ores, iron stones were. So that's another helpful hint to kind of focus your search. So you can fairly rapidly and easily narrow down the broad areas of where we're going to find these. A lot of careful work by Alex on this in terms of looking at historic maps through time. A lot of clever GIS. I don't think I'd have been able to do, but Alex is a bit of a whiz at that. Mapping these out from different eras of mapping from all available sources. And then the sort of second part of your question around, I think is a good one, is are they there? So actually, like in Scotland, there was a lot of ironworks and steelworks around Glasgow, but there's not much slag left here in this area. So I'm not quite sure what the sort of social or economic reasons for that were, but in many places there was lots of iron making and lots of slag produced, but it's not there anymore. And so there was a certain amount of ground truthing that could be through again, kind of using archival records, council records, those kinds of things. Satellite imagery can sometimes be useful. And sometimes you just can't beat going to a site and be like, was there anything there? No, oh well. Or going to a site and be like, this is a strange looking landform, but it's covered in trees and vegetation. Is there any evidence at all? And maybe go back to an earlier question about this kind of like, or linking into sort of geological mapping. Sometimes it is a case of just hunting for exposures. So the example from Glengarnock in Ayrshire that I mentioned, kind of in the sort of social industrial legacy context, that one is interesting. The slag heap is quite big, but it's covered in vegetation and soil, and that commonly happened to a lot of them. They were sort of deemed as unsightly. So when the steelworks closed, buildings were cleared, and then slag left. Doesn't look very nice. Yes. Not good for the environment. We'll put a nice sort of clay cap on it to try and stop any kind of water getting in and then reactions and pollutants getting out and that kind of thing. We'll put a clay cap on it, we'll plant some trees. So that was commonly done. And the Glengarnock slag heap was covered in clay cap with lots of willow trees. But if you hunt about, you can find little exposures here and there. And then like a sort of very thin strip, maybe 2 meters wide at most, along the lake shore, because it was on the edge of a lake. You can sort of piece together with a bit of sort of what we might think was traditional geological mapping, using maybe like LiDAR or sort of available digital elevation models to look for the kind of distinctive landforms that they can often produce as well. So there's a bit of lots of different things coming together to really to do that mapping work. Have a look at the results of the Menti code. So the question then, what is a rock? Let's see. What do people think? Oh, responses are hidden. Okay. So I put up a selection of words. I mean, could have done an open-ended question, but that would be pretty hard to digest. So just, sorry, I'm looking at another computer here rather than sharing on the screen, but I'll just maybe mention some of the results. So the most important, or certainly the highest number of responses for a particular term was made of minerals. Cool. Naturally occurring was the next highest. Compacted, hard, and inorganic, tied, and then the lowest of them was large. Okay, so I mean, I think probably go along with that to a certain extent. Made of minerals. So, unfortunately, I guess we can only ask this question to people in the room. Put your hand up, but if anyone online wants to chip in on the chat. So, what's the most important thing, according to folk who filled in the Menti, for defining what a rock is made of minerals? So, coal, is that who in the room? That's not made of minerals. Coal is not made of minerals, made of macedals and coal. So, who thinks coal is a rock? Would you have thought of coal as a rock before you answered this question? No, yeah, shaking her head. Okay, interesting. Even though we find it in the stratigraphy and among other rocks, not necessarily a rock. Fair. I would agree. It's a weird one. I think you'd often think of coal as being a rock because it's in stratigraphy with other rocks like sandstone and mudstone and limestone and whatever. But you know, made of minerals, yeah, technically. I guess it isn't. Naturally occurring. Well, let's come back to that. That's a controversial one, in my opinion. Compacted, yeah. I mean, that was kind of I suppose you could argue like sort of glacial or clay, you know, like London clay. You know, it's pretty compacted. But it's a sediment, it's not really a rock. So interesting. Hard, fair. Although I suppose salt, like halite layers, so it's quite malleable, flows ductilely in the subsurface. Get these salt glaciers that are known in Iran. So it's not hard, really. But again, a bit like coal, you say, even though you get it as like layers and among other rocks, that's not really a rock. Interesting. Inorganic, I guess that's kind of tied to the made of minerals thing. I probably should have defined inorganic a bit better, but like a bioclastic limestone. Kind of organic, you know, so the fossils in it, kind of, yeah. I put in large, and that may have sounded a bit weird, but the context for having large as one of the terms you could select was if I pick up a pebble from the beach, or I don't know, a sort of grain of coarse sand that was eroded from, I don't know, a basalt, something very fine. So if I pick up that grain of sand, that's made of minerals, been eroded from a basalt, there's multiple crystals in it. It's a rock fragment. But it's like, it's a grain of sand. Is that a rock? It's a rock. If you picked up a pebble at the beach, would you call that a rock? Would you call it a pebble? Anyone got any thoughts on that? Interesting. Thought-provoking. So finally, naturally occurring. So, is that not a rock? Things in this photo here. Like, I could smash that with a hammer, it would not break. Hard as a granite. If you weren't used to looking at slag, you'd just be like, oh, it's and you were just kind of walking along and looking for mud, not looking really closely, but oh, cool, conglomerate, nice, yeah, cool, quite coarse conglomerate. You can see the kind of hammer for scale in the left-hand photo there, Eston hammer. Class size is up to something with 30 centimeters even, it's pretty big. Coarse conglomerate, not rock. Do people, so obviously you filled in the meant it before the lecture. Hands up in the room. Who thinks the photo on the right is of a rock? After what you've heard. A few. Interesting. Well, I feel like that could be a good place to finish. If they remember nothing else, we leave thinking, oh God, what's a rock? Oh, thank you very much. You.
Yeah, I'm just trying to get to the end.
Right.
Yeah. Great. So thank you so much, everyone who's joined us in person today and online. We continue the Off the Rails series and we will be going to Durham next. That will be on the 20th of February with Caroline Cluster, and she will be looking at glaciers and the importance of glaciers for food, energy and water. And thereafter, we will be going to Birmingham in March. And the last but by no means least event in the series will be held at Burlington House in September. And this will be a 2-day conference, which will be pulling together some of the key strands that we've learned across this series. So we hope to see you there. As ever, thanks so much for your time, John. And also we do have our climate lead, who's been highly supportive, joining us remotely. So thank you, Steve. And thanks everyone today for coming. And we will pop a little survey out to you all, which would be really grateful if you could complete and give us your feedback, so we can kind of think about ideas for the next series that we might want to do, or new ideas looking ahead. Thanks a lot.
I'll take this up to you to do that.
Yeah.